Hello, everyone. Mr. Minnick's my name. Math is my game. Today, with a special shout out to Ms. Mandy Arnett for being so awesome. Today, we're looking at Chapter 5, Section 2, Polynomials, Linear Factors, and Zeros. Polynomials, linear factors, and zeros. Anytime I hear a list of three things, the first thing that always comes to mind is lions and tigers and bears, oh my. Remember that from The Wizard of Oz? Okay. So to start this off, I'll give you a second. Hopefully you got the title written down. 5-2, Polynomials, Linear Factors, and Zeros. There's three, I guess it's going to have a theme of threes. There's three ideas that you really need to understand the difference between them. And most of you probably already do. But to get the gist of this lesson, you really need to kind of understand the difference between three things. And those three things are not in the book's notes, but one of them is an expression. You need to understand the difference between an expression and an equation and a function. Okay? They're all going to have the exact same part in them, but they're expressed in different ways. What I mean by that is if we had something like x squared minus 4, that is an expression. There's no equal sign. If we take that exact same thing, that x squared minus 4, and now all of a sudden we draw a rogue line across the screen and we put an equal 0 next to it, then that becomes an equation. And you probably get the idea that this part's going to be in all parts of these. So if I take this x minus 4 again and I want to make it a function, I would write p of x equals. Or instead of p of x, maybe like y equals. Maybe like f of x equals. But the thing is, I do expect that you know the difference between an expression, an equation, and a function, because there are differences as to what you can do with them. Anybody ever go to the garage to have your car fixed and you get tires? And there's tires that are on display that have been on display in the same tire shop for 25 years. Would you want to mount that tire up and put that on your car? The one that's been in the shop for 25 years? Probably not. Okay? So there's certain things that you can do with them. You can look at them, you can get an idea of the tread depth and that kind of thing. And the same thing goes for these. What I'm getting at is an expression, you can factor it. Okay, you can factor an expression. An equation, we could actually factor that equation because that expression can be factored, but with equations, usually the end goal of an equation is to do what with it? Solve it. Good. So with an equation, we attempt to solve it, okay? And with a function, more often than not, with a function, we try to graph it, okay? And when we graph it, we find its x-intercepts, okay? And when we find its x-intercepts, we're kind of doing the exact same thing as solving the related equation. Okay, so finding x-intercepts of a function and solving an equation are the exact same thing. It just looks a little bit different. And that's the gist of today's lesson. That's the big idea, and we've already seen this in Chapter 4. So really, there's not a whole lot of new news. So far, so good? Good. Well, I'd like to go to the internet. I've got, if you can see it, I've got an expression x minus 1. Got the expression x minus 1. And I want you to notice that when the expression's x minus 1, the x-intercept is 1. Okay? If I made this x plus 1, the x-intercept is negative 1. Does that make sense so far? If I make that x plus 3, the x-intercept is negative 3. If I make that x minus 3, the x-intercept is positive 3. Do we kind of remember that from Chapter 4? Okay. So that's a big idea in this lesson today. And it's actually shown right here in this key concept box. Okay. probably not a bad idea to write down the bullet points. You don't need to rewrite what a polynomial is, but I would make light of these facts. X minus b is a linear factor. B is the 0. B is a root. B is an x-intercept. Okay, so x minus b is a linear factor of some polynomial. B is a root, b is a 0, b is an x-intercept. And there's one thing that they kind of left off the list that I would go so far as to add. I would say b is a solution of the related equation. So earlier in the year, I've mentioned the fact that the words roots, x-intercepts, and zeros are synonymous, and they're just restating that. Okay, so x minus b is a linear factor. So b is a solution, b is an x-intercept, b is a root. So it's kind of important, well, it's very important to understand that relationship. The fact that we're talking about factors, we're probably going to be factoring, and you'll see that today. I think a couple of these examples you're going to have to factor. And next week we'll be factoring a lot. I know we only have school 2 days next week, one of which is Tuesday, but we will be factoring on that day. So, all right, so let's go back and see this example 1 that they got for us. I skipped over it somehow. Example 1, they've got this expression. They got this expression, and we can factor expressions. So the expectation is all that stuff that you learned how to do in Chapter 4, you still remember it. Anybody have any ideas what we can do to start this thing? Yeah. Put it in standard form. That's a good start, and it actually is in standard form. So let me just write it a little bit bigger so we can see it. We got x cubed minus 2x squared minus 15x. So it's in standard form. That's always helpful to have them in standard form to start. So is there anything that we can do to break that down? What are you thinking? Yeah, you can pull an x out or factor an x out. This is really xxx, this is minus 2xx, and this is minus 15x. There's a common x in all of them, so we factor an x out. So if we factor out an x, that leaves behind x squared minus 2x minus 15. Now sometimes I feel like I'm an infomercial host. But wait, there's more. We can factor this further. If you remember from Chapter 4, when you try to factor an expression like this, you're looking at the number 15 and you want to know, does 15 have any factors? And in this case, since that 15 is negative, the factors have to have opposite signs. Does 15 have any factors that add up to negative 2? 5 and 3, sure. So that expression, that particular expression right there, factors into something with an x and a 5, something with an x and a 3. What am I going to have to do with the signs there to make a minus 2? Minus on the 5, good. Plus on the 3, cool beans. And then what about that x that's hanging out front? We have to rewrite it. We have to keep it as part of this. Okay, so right there, that's our answer. That is it. That is it. Now this particular problem just says what's factored form. Okay, they didn't say solve this equation, but they could have said solve this equation. What if all that equaled 0? What if all that equaled 0? What if all that equaled 0? What would your solutions be? 5's one of them. Negative 3's one of them, and there's one more. Because of this x hanging out front, maybe we need to go to Desmos to find out. What happens if there's just an x? What happens if there's just an x? The x-intercept is 0, right? Okay. So it is important that x is written, because if we were solving this equation, this factor out here would tell us that one of the solutions is x equals 0. Now we're not solving this, but that's something to keep in mind for later on. Okay, doing all right so far? Good. If we look at the guiding, it's just like the one before. Everybody good with that? Or do you want to try that one too? What do you think? Try it? Okay. So standard form's a good place to start. X cubed minus x squared minus 12x. Can we factor anything out? X, sure. So we factor out an x, which leaves x squared minus x minus 12. And wouldn't it be nice if 12 had factors that added up to negative 1? Oh, 4 and 3. That'll get it done. So we got an x and a 4, an x and a 3. And we just got to figure out our signs. And if you forgot about the signs, since that's negative, that means that whatever these are, they have to be opposite. One has to be positive, one has to be negative. Positive on the 3, yeah, and the negative on the 4 will get it done. Cool beans. So there is our answer. So far, so good? So what do you think about chapter 5? It's chapter 4 again. Just with a little bit more stuff. And we'll see what that's about in a few weeks' time. All right, factor theorem. This says the same thing we said a minute ago. So I'm not going to ask you to rewrite it, but it's very important that you know. They're saying x minus a is a factor of a polynomial if and only if a is a 0 of the related polynomial function. Okay, so just understand that relationship. Understand that relationship that if you have f of x equals x minus 2 times x plus 3 times x minus 8 times 3x plus 4 times 3x plus 4, that the zeros of that function would be, let's see if we can figure these out. I have a feeling we'll be good on most of them. This factor of x minus 2 tells us what is a 0. 2, good. This factor of x plus 3 tells us what is a 0. 3. Or 3 or negative 3? Negative 3, cool. This x minus 8 tells us what is a factor, or what's a 0. Positive 8, good. Be careful on the last one. Maybe we should go to Desmos. 3x plus 4. 3x plus 4. So because of this, what's our other 0? Negative 4/3, good. It's negative 4/3, negative 4/3. But where'd that come from? Well, let's see where that came from. 3x plus 4 by the 0 product property would equal 0. So when we solve, we'd have to subtract 4. So we get 3x equals negative 4. And we'd have to divide by 3 and divide by 3. So that's where that comes from. Okay. What do we think? Got him? Okay. Again, this is really nothing new other than the fact that instead of having 2 zeros with polynomials, we're going to have a lot more sometimes. One thing I'd like to consider is what happens if we have something like this? What happens if we have x minus a, the quantity squared? Let's take a look at what that looks like. Suppose we have x minus 3. We know there's a root there when x is 3, but what happens if we take this quantity and we square it? Let's explore that idea. When we square that, it's kind of weird. We know that we have x minus a times x minus a, so the zeros would be a and a. Isn't that kind of redundant to say? Isn't that like saying the same thing over and over again? Isn't that like repeating yourself? Isn't that like just saying what you just said? Look what you made me do. Look what you made me do. Look just what you made me do. Look what you just made me do. It's like that. Very repetitive. Anyway, the deal is the graph, and this is worth noting, the graph behaves. The graph behaves. That's so weird to talk about the graph behaving. Graph, you be good. The graph behaves quadratically. The graph behaves quadratically. The graph behaves quadratically. Why quadratically? Because of that exponent of 2. Because that's what we studied in chapter 4. Quadratics are parabolas. The graph behaves quadratically. The root occurs twice. It's so weird for a root to occur twice, but it's pretty clear if we break the factoring down that it does occur twice. It's a repeated solution. Okay? The root is repeated. It's repeated. So some language that comes up is how many unique roots does this function have? A function could have 7 roots, but it might only have 2 unique roots. It might have a root of 3 6 times and a root of something else once. Okay, so this brings up a really cool word that's kind of fun, and we'll see what that's about in a minute. So normally I don't take this to the next level. I don't think we've graphed a cubic function yet. Just so you know what a cubic function looks like, it kind of looks like this. So if we had x minus a, the quantity cubed, that would be x minus a times x minus a times x minus a. And you could probably guess how the graph's going to behave whenever there's a root that's repeated 3 times. Let's take a look. Desmos to the rescue. X minus 3 cubed. Notice how the graph behaves there. The graph behaves cubically. Okay. So in a case like this, the graph behaves. You be good, graph. Cubically. Not many 5-syllable words that we use. In the English language, we use a lot of 1-syllable words. Monosyllables. Yeah. Okay. Fine. Good. Yup. Yes. No. We use a lot of 1-syllable words. How about this for a 5-syllable word? Multiplicity. Multiplicity. Suppose we have something like this. P of x equals x minus a, the quantity, squared, times x minus b, the quantity cubed, times x minus c. Something like that. Okay. So the question might be, what are the roots and state their multiplicities, their multiplicities? So this multiplicity, this just means repeated roots. Repeated roots. So when we talk about their multiplicities, we're really talking about the number of times it is repeated. The number of times the root's repeated. So if we look at this example, this p of x equals x minus a squared times x minus b cubed times x minus c. This factor tells us that one of our roots is what? A. With a multiplicity, of what? Of however many times that the 0 repeats. Twice. So it's a multiplicity of 2. And this factor tells us what else is a root. B with a multiplicity of 3. And this tells us what else is a root. C. And here's the thing. If there isn't a multiplicity, there's really no need to say it. Just like if an exponent's 1, there's no need to write it. Or if a coefficient's 1, there's no need to write it. Or a denominator's 1, there's no need to write it. If there's no multiplicity, there's really no need to write it. How do we feel about multiplicities? Got it? Cool. There's really only one other big idea in this lesson. So let me back this thing up and see if I missed anything that the book wanted you to get out of that. Okay, so here they're talking about these multiple zeros. Ooh. Oh, man. Problem 4. I'm kind of going out of order a little bit, but that's okay. What are the zeros of this function, and how does the graph behave at these zeros? Wow. I hope I could factor this. F of x is x to the 4th minus 2x cubed minus 8x squared. Can we factor anything out of this? X squared, good. So we can factor an x squared out, which leaves behind x squared minus 2x minus 8. 8's got factors that add up to -2, right? 4 and 2, so an x and a 4 and an x and a 2. We need to figure out those signs, and we still got this x squared kind of hanging out front. What are those signs going to be? -4 and +2, good. So what are the zeros? Well, the zeros are going to be 4 and -2 and 0 with a multiplicity of 2. 0 with the multiplicity of 2, 4 and -2. How are we doing? Question. The multiplicity comes from the fact that we have this exponent of 2. Dang it. This exponent of 2 on that particular factor. Anytime we have, like that factor, that x squared, that's really x minus 0, the quantity squared. So anytime a factor has an exponent other than 1, there's going to be a multiplicity there. That's a good question. Really good question. Do you guys remember the TI Inspire? The calculator back in the day when we used to use those? Sorry, my writing's kind of sloppy down here. This is 0 with the multiplicity of 2, if you're trying to figure out that one. 0 with the multiplicity of 2, 4 and -2. So on my Inspire, there used to be this command that I could enter. Anybody remember the magic command if I wanted to find the roots of a polynomial? Oh yeah, poly roots, parenthesis. So I needed the expression x to the 4th minus 2x cubed, thank you, minus 8x squared, awesome, thank you. Now there was something that I had to do at the end of this expression. Anybody remember? Comma x. You guys have brought your A game, awesome, nice job. So there it is, -2, 0, 0. Look what you made me do. Look what you made me do. Look just what you made me do. Look what you just made me do. It's repetitive. Like every pop song on the radio, the chorus goes on for 3 minutes. Look what you just made me do. Look what you just made me do. All right. How do we feel about that example? We got the idea? Okay. So later on in the chapter, what's going to happen is we're going to get polynomials of degree 5 or of degree 6, and we're going to have to find all their zeros. And there's special ways that we do that if they don't factor easily. So that's kind of a roadmap of where we're heading. So I said there's really only one more big idea. And that last big idea goes back to this last example here. And we'll do all of problem 3. There's a part A to it and there's a part B to it. It's kind of cool. They're saying, what's a cubic polynomial? And this part right here just really grinds my gears. This part right here grinds my gears. If they didn't say that, this would be really easy to do. But the fact that they said it in standard form, that means it's time to go to work. It's time to call up our social studies teacher who knows how to make these happen. We're going to have to use that FOIL method. So in factored form, this is quite simple. Factored form, we would have y or p of x or f of x equals. Now let's take a look. -2 is a 0. So what's that mean a factor is? Not just 2, x plus 2. Good. X plus 2. X plus 2. And because 2 is a 0, what's another factor? X minus 2. Good. And then because 3 is a 0, our other factor is x minus 3. So if they said just put this in factored form, that's good enough, and we could stop there. But did they say factored form? No, they said standard form. Dang them. Why did they have to say that? Just ruined my Thursday. So this is going to be x squared plus 2x minus 4 times x minus 3. Hey, wait a minute. What happens with that plus 2x and minus 2x in the middle of that one expression? They cancel. That's kind of cool. That's pretty boss. So that's x squared minus 4 times x minus 3. And again, I told you, our social studies teacher down the hall knows what's up. FOIL method. So this is going to be x cubed minus 3x squared minus 4x plus 12. And that's what y equals. And that's the way the cookie crumbles. Is it any surprise that we have a degree of 3 when there's 3 zeros? Shouldn't be a surprise. That's the fundamental theorem of algebra. That's the fundamental theorem of algebra. So in the exercises, when they say, they're not even going to say in standard form, they're going to say with integer coefficients. So note to self, when the directions say with integer coefficients, that the implication is in standard form. Okay? So in standard form or with integer coefficients, those directions mean the same thing. Okay? So in tonight's exercises, they will tell you with integer coefficients. Means the same thing as putting it in standard form. Means the same thing as instead of just writing out it in factored form, you do have to do the expansion here. Questions so far? Almost done. Number B. So number B, same idea. Y equals, what's our first factor going to look like? X plus 2 quantity squared. Nice, good one on you. X plus 2 quantity squared, and then X minus 2, and then X minus 3. Cool beans. Cool beans. Everybody multiplies things in a different way. With this particular one, I'm going to just expand this x plus 2 out twice, actually. You'll see why in a minute. The reason I expanded that out is because I like what happens when I multiply this by this. That's the difference of 2 squares, remember? And that middle term drops out. So that's kind of why I'm going to do that. So that's going to give me x squared minus 4, I know. And just to save a little bit of space, I'm going to go ahead and FOIL this x plus 2 with this x minus 3. And I'm just going to go ahead and write that expansion over here. So that's going to be x squared. The outer product's minus 3x. The inner product is plus 2x. So what's that going to give me in the middle? Minus 3x plus 2x. It's going to be a minus x. Good. And then on the last term, it's going to be minus 6. Cool. And I'm left with that to multiply out. Oh, man. So when I do this, I guess I'm going to take the first 2 terms to the first term first. So I'm going to get x to the 4th minus 4x squared. So I'm done with that. And then I'm going to take the first 2 terms to the next term. So that's going to be minus x cubed minus 4x. No, plus 4x. Yeah. And I'm done with that one. And then lastly, I'm going to take the first 2 terms to the last one. So that's minus 6x squared, and then plus 24. And now I'm left with the chore of combining all my like terms, right? And there's really not many like terms there. So here it is. y equals x to the fourth minus x cubed minus 10x squared plus 4x plus 24. Wow. The last thing, and this is it for the whole lesson, they want us to graph these and see how the graphs are the same and how the graphs are different. So if I go back up to that first one, I wrote everything in blue, I think. So I use a blue crayon when I graph that. I know my roots there were -2, 2, and 3. -2, -2, 2, and 3. Let's see who remembers anything at all about end behavior. Remember that from a couple weeks ago, end behavior? The leading coefficient's positive, which means the graph is going to be going up on the right. The degree is odd, which means the graph is going to do what on the other end? Heading down, right? So the end behavior, that's going to be down and up. So the end behavior, this is going to be down and up. And the y-intercept of that is going to be 12, right? The y-intercept of that is 12. So if I had to graph that particular function, it's probably going to look something like this. Woo! Something like that. Right? And if I graph this red one, red, -2, -2, there's a 0 at -2, and another one at -2. Oh, man. And then the other one is at 2 and 3, same places. What's the end behavior of that one? What's the end behavior of this one? Up, up, good. It's going to be up and up. So that one is also going to be going up on the right. And it's probably going to go through here. Woot, woot. And its y-intercept was 24. So it's going to go up way more high. And it's going to come down to here, and it's going to go woot like that. And it's going to look like a parabola there. Right? You like the sound effects? Kind of reminds me of SpongeBob blowing the bubbles. First you do this. So I'll just go to Desmos real quick to confirm what we've got, and then that'll be it. So this was x plus 2, x minus 2, and x minus 3. Okay, so we did pretty good with that one, huh? And then the next one was the quantity, x plus 2. That quantity was the squared quantity times x minus 2 times x minus 3. Hey, the graphs actually aren't bad, huh? Not bad. Any questions, comments, concerns about polynomials, linear factors, and zeros? About lions and tigers and bears? About look what you just made me do, look what you just made me do, look what you just made me do? I promise I'll try my very bestest to never sing that song again. Not that I sang it, but anyway. It's been real. It's been fun. Have the best day of your lives. Good.